Good evening, everybody. It's an honor and privilege to be here, standing here and delivering this presentation. Also, good afternoon to people who are logged in online. Thank you very much for joining. So today I'm going to walk you through I'm going to talk about ship electrification solutions. I'm not going to talk about future fuels. So when I say ship electrification solutions, then what options, what solutions we have under ship electrification solution? What do we offer for the marine market? Can anyone guess how many vessels do we have operating globally? Just a guess. 20,000. Very close. We have close to 100,000 ships operating globally. And as we know, shipping contributes, accounts to 3% of global greenhouse gas emissions. Now, when we say 3% of global greenhouse gas emissions, then the number sounds very less. It's just 3%. But in terms of carbon emissions, we are talking about 900 metric tons of carbon being thrown in the atmosphere. The good news is the ship owners, operators, they are scrambling to find a solution. They are scrambling to start chalking out a roadmap to decarbonize their operations. But the big question here is decarbonization only about future fuels? And as we know, we don't have one size fits all solution. And shipping being vast in nature, the solutions what we offer have to be viable and technically feasible. More so, we have so many segments in shipping. Every segment would require a different solution. Meaning, when we talk about seagoing ships, merchant ships, we can't put batteries on that. It has to be hybrid or it has to go on future fuels. But when we talk about passenger ferries, then hybrid, then full electric solutions, full battery electric as well as hybrid is much more feasible solution, and it is doable. So we will now dive into our presentation. So as a company, our purpose is to enable sustainable societies through innovation in technology and services. Key strategic priorities is to drive decarbonization in marine and energy markets. So decarbonization, as I said, is not about only future fuels. It's a combination of engine optimization, fuel flexibility, the electrification, energy-saving technologies, and voyage and operational efficiencies. Now, if you look at the global new build market data, it has doubled in 2021 and 2022 from 900 ships to 1,900 vessels per year. The good thing is electrification share is increasing. So if you look at the graph, the bar chart, it's obviously led by two-stroke, the large vessels, seagoing vessels, followed by four-stroke. And then you see diesel electric share is also increasing. Then we have batteries and diesel and full electric propulsion. So diesel electric is still a niche, but it is reaching new segments. Right now, diesel electric is very popular in towage and offshore, but it is actually getting popular in other segments as well. Diesel mechanical, as I mentioned, it is dominating in large vessels. However, the electrification is taking place via PTO, PTIs, and every second system comes from us. Presently, full electric vessels are only popular in small passenger ferries. except the large 130-meter, which is being built by INCAT Tasmania, where we are supplying the entire drive solution for that ship. In battery and diesel, we are also market leader here. We are close to 20 vessels from us, and the number is still growing. We say we electrify shipping. Now, when we talk about hybrid market leadership, then it took 10 years to get 100 megawatt of batteries on ships, but the second 100 megawatt hour happened only in 2023. We have now close to 26% market share in hybrid ships based on battery size and 16% based on number of vessels. Recent reference success stories, here are a few success stories, such as 10 vessels for Grimaldi, which is Italy-based ferry operator, mainly pure car truck carrier. One INCAT Tasmania, full electric. Second is Stena E-Flex, and 5 to 20 VETA full electric ferries. VETA, the full form of VETA is Water Emergency Transport Systems Authority, which is based in California. So we are designing the whole integrated package for them. And the number of vessels are up to 20 vessels. Now, when we talk about shaft generator leadership, it took 50 years to get 500 vessels with our shaft generators, and just 2 years for the next 200. So you can very well make out, how the industry is bracing for the new technology and electrification on their ship designs. Every second shaft generator with relevant size greater than 1 megawatt in fleet comes from us. Market share in China and South Korea is growing because that's where the maximum new build is taking place for the large vessels. Recent reference cases is 12 CMA, CGM commercial vessels, 5 Venture Global LNG carriers, and 8 Union Marine tankers, and 16 Evergreen commercial vessels. We like to push the boundaries. Now, when we talk about hybrid, pure car and truck carriers, then we have supplied the largest energy storage system to Grimaldi, which is 5 megawatt hours. On top of spinning reserve, peak shaving, also it gives you a flexibility to operate the ship on zero emission in port. Moving on to RoPax, they are going hybrid currently. Most of the designs are hybrid mechanical. So the example is Brittany Ferries, Stena, where we have supplied 11.5 megawatt hour of batteries. Now, this allows full power at maneuvering only on batteries. So again, it gives you a flexibility of zero emissions in port. Then we have also supplied IEC show power for charging. Then moving on to the full electric ferry, which is being built right here in Australia by INCAT Tasmania, which is 25 knots, the maximum speed, with 40 megawatt hour of batteries, which this ferry can carry 225 cars and 2,100 passengers. We have 16 megawatt propulsion power via 8 water jets. It's a 2-hour crossing one way, and the turnaround time is 90 minutes. I'll give you more details on this particular project in the following slides. This also has a DC charging at both ends. Now, here are the 3 different propulsion configurations which are mainly popular in ship design. One is mechanical FPP. Now, here we have So here we have engine as a prime mover connected with a gearbox and driving the propeller. Then we have the genset pumping the power to the switchboard, and that is operating your tunnel thruster or transverse thruster. Then we have hybrid mechanical CPP, where we have, again, engine as a prime mover. Then we have K-box, we have PTI, PTO, and the K-box is driving the propeller. As you can see, hybrid mechanical CPP has a battery pack and a genset. So the genset is pumping the power to the AC switchboard. Then it gets converted. It goes to the DC switchboard. And there are batteries which are also connected to the DC switchboard. And based on the operating profile, you can basically switch to batteries from the engine when engine is not required, especially maneuvering. And you can also see there is an LNG pack or ammonia-ready ammonia pack, just in case if your engines are on future fuels or on LNG. Then we have hybrid electric, where we don't have engine as a prime mover. We just have PM motor. And then we have battery packs and the auxiliary gensets, which are pumping the power to DC switchboards. And all the operations which is happening in this particular setup is all managed by batteries and the auxiliary gensets. So the question is, why electrification? So the large portion of electricity in grids is already getting green. National grids will have high percentage of green energy sources, as we know. Whenever a vessel is using and charging electricity, this reduces CO2. Most ports will have shore connection option in the near future. There are ports which are making this compulsory. So this point is an important point, and I think in future, very soon, this will be applicable to more and more ports globally. This will be a standard design on a design feature in the new builds, which is already happening. We have shore connection options being already put in the design right from the new build stage. Why hybrid systems? So hybrid system, it makes use of various energy and storage system to optimize the operations. Even temporarily sail or stay emission free in the port, as I mentioned in my earlier slide. So it's a combination of engine, it's a combination of alternate fuel, it's a combination of batteries, heat recovery. So all in all the system, when they come together, it makes an optimized system, and which is practically doable in present times already. So when we talk about hybrid vessel and incorporating the batteries, it's not just connecting the batteries to the system. Basically, the energy management system and power management system plays an instrumental role for an optimized and efficient operations of the whole system. They are not available on the market like plug and play. They are only available with the experienced hybrid integrators. A normal power management system can only turn the battery on and off a hybrid vessel and will not deliver its function. A normal PMS, power management system, cannot safeguard charging, discharging speed that is so important to keep battery life as engineered. So at times, there is a demand from the market or from the shipyard that, we supply our engines and they supply the batteries. But then in that process, we have to also take the lifetime of the battery and, lifetime of the battery into consideration, because the battery management system, power management system plays a crucial role for the entire system to perform in an optimized way. And when the system is optimized, it means that the longevity of the batteries is also optimum. Otherwise, there is a lot of losses. There may be losses in the system if it's not integrated properly. All vessels will be hybrid at some point. Already today, there is a positive return of investment. As you can see in the matrix, the impact on the fuel consumption in the various types of vessels. The PSVs reduces the fuel consumption by 25%, followed by bunker vessels, followed by shuttle tankers, and then we have pure car and truck carriers reducing fuel up to 7%. So this reduces the installed power. So that's one of the main advantage of hybridization. It optimizes the vessel operations by hybrid functionality. So it plays between the batteries, the auxiliary gensets, the PTO. So it's all like, it's sharing between all the systems what are installed in the whole hybrid package. Hybrid also optimizes the vessel operations with new power sources, additional variable loads. It also gives you a flexibility of zero emissions operations, for example, close to the port or in the port. Get partly green energy from the grid via charging. Now, this is the project which is much talked about in the recent times. It has attracted a lot of attention globally. So this is world's largest full electric high-speed craft, which is being built by INCAT Tasmania. And as I mentioned, the whole electric package, the drive solutions are being provided by Wärtsilä. So as you can see, we have 41 megawatt hours of batteries. We have battery short circuit limiter. Then we have DC hubs driving 8 e-motors. These are permanent magnet motors, which are driving 8 water jets, that is the type of water jets is 1100, WXJ 1100. And you will see a very different design here. We have 8 water jets where we have 4 steerable and 2 booster jets. These are mainly to optimize the weight on the ship. Then we talk about Wärtsilä energy management. In my earlier slide, I did mention that it's not easy to procure the different systems and then, do not give that to integrate to that one integrator. Because energy management is extremely important here for an optimized operations of the whole system. We are also supplying automatic charging systems, shore infrastructure to the end user in South America. So what are the considerations when we were designing this ship together with INCAT? So the operating profile is important. The route, the speed, the range of the ship, the sea condition, service routines, the vessel requirements such as weight, maneuverability, hotel load, redundancy, and classification rules. So these are extremely important when you actually design the battery. So the solution on shore is we are supplying, as I mentioned, the automatic charging system. And this is going to be DC charging. So there are DC conversion e-houses on shore. So the power which goes on the ship is the DC power. The route is between Argentina and Uruguay. So this is roughly 2 hours one way. And the ship is also having a redundancy just in case if they could not charge, then the ship can go back with the reduced speed and then charge at another point. So another considerations for the show was the charging time, the key facilities available there at both ends, the grid access, the grid capacity at the moment, energy cost, which is extremely important to make this business case feasible, and also considering the environment. Now comes to the life cycle. Now these batteries basically do not require much of maintenance like normal engines, reciprocating engines, but we do have the Wärtsilä monitoring system. We call it Wärtsilä Expert Insights, where we see the whole system versus the battery. We also have life cycle agreements, which assures the asset uptime. Then there is also a flexibility of route and schedule. And then obviously spares and service. Now, here are a few full electric references from Norway, where we have been designing, we have been doing the SLDs. Now, this project is basically, the owner is Columbus in Norway, and the route is Stavanger to Hommersåk. Shipyard which built the ship was Fjordstrand. Now, this particular boat was basically a part of TRAM project. The full form of TRAM is Transport, Advanced and Modular. So this is a EU-funded project. EU has funded 12 million euros. And the main purpose of this Transport, Advanced, Modular was to basically reduce the construction cost by having the modular design and also reduce the engineering cost. So as you can see, we have 762 kilowatt hours of batteries. Then we have the shore charging station. And then we have DC hub driving, we have inverters converting DC to AC, and then we have thrusters and the propellers. So the maximum speed, this is the fastest full electric ferry available in the market as of today. The maximum speed is 72 knots. The length is 30 meters. Width is 9 meters. Battery capacity is 1.5 megawatt hours. It has 2 electric engines, 2 into 550 kilowatts. The charging capacity is 2.3 megawatts. The name of the ship is Medstrom. Another reference is again from Norway. This is the operator of these two boats is Boreal. The route is Lons to Kvelandstrand and Abelnes to Andabeløy. Here again we have 2 ferries, which is 30 meters and 50 meters. And as you can see, we have two battery packs and then 1 emergency generator of 500 kilowatts. We have DC hub, inverters, and then we have motors driving the propellers. Now, jumping onto the battery chemistries. As we know, the lithium-ion batteries are getting more and more popular in present times due to their capacity to store large amount of energy. However, if these batteries are not used properly, it can also pose a risk, which we will see in the next slide, following slide. Now, as of today, there are 3 battery chemistries which are available. One is NMC, nickel, manganese, cobalt. Now, this is one of the most popular batteries as of today because of its power to weight ratio. high energy density. So these are available in both options, air-cooled and water-cooled, up to 6C, typically 2 to 3C. It can go up to 5,000 cycles, DOD, depth of discharge of 60%, deteriorates faster below 80% state of health. Then we have LFP, lithium phosphate batteries. It's a newer chemistry and it is actually gaining popularity. It is more safe because there is no oxygen in the chemistry. Often 1C, but also 3C is possible. It can go up to 6,000 cycles. Steady deterioration over the lifetime. A bit bigger footprint than NMC, but it comes with its own advantages. Then we have another chemistry which is called as LTO, again gaining popularity, lithium titanate oxide. It's a special chemistry patented by Toshiba and being manufactured by battery maker based in Sweden, which is Enchandia. Expensive, very safe, hard to get thermal runaway produced because the component it has, the chemistry it has is much more stable. It can go up to 20C, high number of cycles. So the battery will be much smaller for comparable operating profile, obviously. Fits for crane operations, short trip ferries with many full discharges a day. Meaning, imagine if there is a ferry which is plying between point A to point B, does 20 trips a day, and you don't want to charge, and the turnaround time is only, let's say, 15 minutes, not possible to charge, then this is the better option. It gives you a high number of cycles. Now, we will understand now in this slide the terminology of when we say modules, when we say cells, when we say rack, what does it mean, basically? So a marine battery rack consists of cells, modules, packs, or strings. So they are either flat or cylindrical. A module has the cell inside that are packed in a way to avoid thermal runaway. Each module has certain current and voltage. So it's not that one piece which is giving you the voltage what you desire. Basically, it's all connected in series, getting to that required voltage, and it can also be connected in parallel. So each module has a certain current and voltage. A string pack is then created by adding the modules up to reach the ideal DC voltage of 1000 volts. Each string pack has its own controller. The size of the battery is then created by adding strings into a rack. So there is a rule of thumb if you have to dimension it. So for 1 megawatt hour of batteries, it's close to 10 tons, 10 cubic meters. The rack dimension could be 7 meters by 2.5 by 0.6. Now you can see the figure here on the left-hand side, how it looks. So these are some definitions. Batteries are also often called energy storage system, ESS. So these are some terminologies which are used when we talk about batteries. SOC is state of charge, is the percentage of the energy remaining in the battery. C rate, current rate, the rate of charge or discharge expressed as a function of the rated capacity. DOD, depth of discharge, is the percentage of the energy removed from the battery. State of health is the remaining capacity as a function of the capacity when the battery was new. BOL, EOL is beginning and end of life. The battery is designed that is can do the same BOL as EOL after EOL. we either miss power or energy. So this is the sizing examples for two major use cases for hybrid vessels. So the application first is spinning reserve. So battery acts as a virtual generator and prevents a blackout if genset is failing. It eliminates need to run additional gensets for safety reasons, saves fuels by better SFOC of high load genset. So how do we do the size estimation for this? We take the kilowatt of genset to be replaced. Let's assume we need 3C battery for battery power. We divide that by 1000 kilowatt by 3. Let's say we need 60% DOD depth of discharge for an NMC battery. Then we divide 1000 by 3 by 0.6, which gives us 555 kilowatt hours of batteries, which needs to be replaced for the genset. Another is zero emission operations. So battery is driving the vessel or part of, let's say, a thruster as well. We take kilowatt power unit to sail the vessel, let's say 2000 kilowatts. Then include the time. Let's say we want to use that power for 1.5 hours. So we multiply, we include 80% depth of discharge for an LFP battery. We multiply 1000 into 1.5 divide by 0.8, which is 1875 kilowatt hours. Now, this is a touchy subject, because this is much talked about when we talk about lithium-ion batteries, the safety aspects. As I mentioned earlier, if these batteries are not used in a proper way, if they are not designed in a proper way, then it can pose a risk. But the classification societies, integrators, ship designers, they are actually ensuring the safe use of the batteries. There is a safety data sheet as well. The component that make up safety system for the battery and space are battery management system. It is extremely important for an efficient and safe operation of the whole system. Thermal management system, electrical protection system, gas detection system, fire detection system, fire detection and suppression system, and ventilation system, environmental control system, and emergency disconnect system. So these are few systems which are actually deployed when you actually design a battery for a ship. Now, I want to give you an example here. Now, what are the common hazards when we talk about battery safety? So thermal runaway is one thing, but very, very important thing. The another thing is sudden rise in the voltage, which can damage the electronic devices on board. Now, thermal runaway, as we know, is nothing but if the current is passing through the cell, there is a rise in temperature, which further raises the current in the system, and then which further raises the temperature of the system, and which can lead to fire. Now, if there is a fire, then we know that these are liquid state batteries. So the electrolyte, there is a chance of leakage, which converts them into toxic gases with toxic compounds which are coming. So we need gas detection system. And now I want you to imagine, just for a better understanding, basically, that consider this room as a module. Each chair is a cell. So if there is a fire in one cell, so the battery makers, all the battery makers, they actually have incorporated a system which restricts the fire within that cell. So as soon as there is a fire, it detects, and then that system is flooded and completely isolated, so that that fire is not propagated to the adjacent cell or the module. And designing of the fire rated insulation arrangement of the boundaries of the battery space and the adjacent machinery space should also contain the fire so that it doesn't propagate to the adjacent compartment. For imagine, let's say this first row catches a fire, so it should be designed in such a way that the fire do not propagate to the adjacent compartment. Moreover, from an economic and ecological standpoint, the battery makers are also working on this 3R principle: reduce, reuse, and recycle. So this has positively affected the development of the safe and sustainable battery system for the industry. Finally, fast charging is also being developed to reduce the charging time. Now, this is also a subject, which we can talk some other day, but presently we are using CCS, combined charging system, for charging. It's a DC charging. Now, this type of charging, combined CCS, it can take close to 350 kilowatts. It can carry 350 kilowatts and 500 amperes, which takes a longer time to charge. Now, due to high demand, they have been deploying 400 kilowatts of chargers. And what we know is they're also working on 700 kilowatt capacity as well, in order to fast charge the system. Another game changer in the charging area could be MCS, which is again under development, megawatt charging system, which can charge at the rate of 3.5 megawatts with 3000 amps. But it is still under development. So what we offer when it comes to shore infrastructure. So we offer alternate marine power, which is also called as cold ironing. So vessel takes the electricity when in port and shuts down all engines. This reduces the local emissions and fuel consumption in port. Is already standardized in IEC 8005, that all commercial ships and ports can easily connect. And this is going to become compulsory in time to come. Highest adoption of high voltage solutions, which is 6.6 kV or 11 kV. Then we have charging, as I just explained, which we also offer. So vessel takes the electricity when in port and recharges the batteries. It also allows vessels to sail zero emission for some time. Typically used in closed infrastructure, not standardized yet, but it's a custom for each project. I think with this, that's the end of the slide, or end of my presentation. So we always say that what can go electric will go electric in the future.